Hello, and this will be the second part of the Ghidra tutorial that we started 2 weeks ago. On this tutorial, we'll see an actual example and how a vulnerable binary looks like. So in order to start, we can look on a simple binary that looks like this. So here we have just a character array of 64 byte size, and we can actually make it smaller so that it can be easier for us. So let's say we can make it 32 bytes. And then the vulnerable function gets. So gets function is just copying a string from the input to the actual pointer that is given. This is the manual page, and so when we compile this binary, we will actually have a prompt, and then we copy the data that we want there, and it gets transferred to the 32 byte size buffer array. The problem with this function is that it is copying data until it encounters a null byte, and it is written here actually. No check for buffer overrun is performed, so this will be the actual problem. And it says here that gets reads the line from SD into the buffer pointed to by S until either a terminating new line or end of file, which it replaces with a null byte. So it will copy data until it encounters an end of file or a null byte. And we can move on and compile our binary. Yeah, we can ignore the implicit declaration. So here again, we created a toy project on which we will actually load the actual binary. So this is the binary file. We importing it again. We'll leave the default things here. And we open it with a code browser. So as you can see, we have the functions here, there's 20 of them, and the entry point is our main function is actually this one. The binary in this case is not stripped, and you can check it from here. That is a not stripped binary. So we actually have the symbols here, and we can look in the actual function. Okay, so I lowered the resolution so more people can actually see. So this is the main function here, and the disassembly, and here is the output from the compiler. You can see here is the place where get is called, or here. These lines are actually related to checking the stack for if the stack cookie is corrupted. And this local 30 variable is the point, the address of the 32 bytes table. So you can rename this as local. So we don't actually care about this. The only thing we care is this line where gets is called, and local 38, which is our actual buffer. So in our example, the actual car array is 32 bytes, or 0x20, but this information is not maintained after compiling the source. So here the buffer is identified as a 40 elements, an array of 40 elements. That's why the size is different here, because the decompiler cannot detect the size of this variable. It gives you all the space that lies between local 38 and local cookie. So if you want to see where local 38 is placed, you can go here on the listing view and look just after the function signature. So here I'm talking about this information. So this is the first part of the function, and you can see here that the return value is identified as 1 byte of and this byte will be on the RAX register, which is AL is part of the RAX register, and it's 1 byte in size. And after the return value, you can see these 4 local values. So these values are allocated on the stack. So here, for example, the size of this value, the local cookie value, is identified as an undefined 8 byte size, and it is placed at minus 0x10. So at this offset, there is the local cookie variable, and this actually works in a way where this variable is referenced from usually using the RBP register. So RBP register is the frame pointer register, and here you can see that if you click on the RBP here, you can see that it is used with some offset. So RBP plus local 3C, local 48. So wherever you see these variables here on the listing view, it is actually replaced by the offset that you have. So it's local 3C. The actual disassembly is the actual instruction is RBP plus RBP minus 0x3C. So it's so Ghidra is doing this in order to help you in a way. And instead of tracking by yourself, it replaces these offsets with their names, and their names are actually these offset values, but local is because it's local allocated on the stack. It's some sort of local variable in the function, so where it can only be referenced inside these functions. So here you can see that gets is called against with an argument, and this argument is local 38. So the pointer that gets takes as the only parameter that it is the address of local 38. And in order to see that, you can see on the listing view where get is called, and there is some sort of sequence where the variables are passed to every function. So for example, on Linux, it is actually called an ABI, an application binary interface, where it specifies which registers to be used for variable passing purposes, which registers are not maintained across function calls, and other types of stuff. So on Linux, the first parameter is passed on RDI, and every time there's a call, the first argument is passed on the RDI function. In order to see that, you can actually see this instruction here, and this is only for 64 bits, not 32 bits. In order to see that, here you can see the actual value getting transferred into RAX. So in this line, the whatever is the address calculated by RBP minus 0x30 is transferred into local 38 variable, so it is actually the RAX register, but for convenience it's referenced here also. So in order to change this, if it is bothering you, you can go here, on operands and operand fields, and uncheck the markup stack variable references. I think no. Yeah, so it is this the always show primary reference. So now the local 38 is not, you don't see that here on the listing view as a name for RAX. So RAX is loaded with the address of RBP minus 0x30, and then RAX is transferred into RDI. So because the local buffer is allocated on the stack, we actually take the address. So we use the load effective address instruction, and not the mov that moves that around. So this is loaded into RDI, and then get only takes one argument, and this is the argument get. Whatever leaves into RBP minus 0x30. Now if you double click the get function, you get transferred to the thank function, which is an 8-byte. This is actually replaced by the dynamic the loader, the dynamic linker. The first time you call get, the actual address of this function is copied here, so it is used every other time that you use it. So we can go back to our main function. So yes, we call get function again with this argument, and the reason it is vulnerable is because it never checks for the input if it is smaller than the actual size of the buffer. So if we actually run the function, the example software, and we input, let's say, we feed it with 100 characters randomly. It terminates by saying stack smashing detected, and it actually aborts, and this actually ends up calling this function that you see, the stack chk fail, because 100 bytes are written into the local 38, actually 101, because it's a new line too. And if you look at the local 38, it's actually yeah, this is the address of the buffer, and here Ghidra identified it as size 40, but it is actually 20 bytes. No, 32 bytes. So we write 100 bytes where 32 bytes are actually written, are reserved. So after that, we move on corrupting other data on the stack, because get is not able to detect this overflow that occurs. So after in order to see what is corrupted, you can pay attention to the listing view. So at first, here the actual RBP is set here on this line, and takes the value of the RSP, the current ISP, and then RSP is decreased by 0x40 bytes. So the address that we get is calculated here, and it is RBP minus 0x30. And you can see here on the call stack the actual offsets of the variables. So we are setting from RBP minus 0x30 all the way to RBP plus 0x something. So we actually add 100 bytes to this value, and the actual space for this variable is from 0x38 all the way to 0x10, and here you can see why Ghidra identified it as 0x28 size, because there's nothing in between these two variables here, the local 38 and the local cookie, which is used. So this offset is used and then this offset is used. So Ghidra says, okay, then local 38 is 0x28 bytes because nothing else is used in between. But you can actually go, this 8 bytes that is 8 bytes more actually is for alignment purposes. So you can go here and where is it? Retype this variable, and instead of saying 40 bytes you can say 32 bytes. And then Ghidra changed this the size of the variable to the actual size. So now if you want to find out why this is crossing, it's because when we start overriding the local 38 variable, after 40 bytes it starts overwriting the local cookie. So if we use 39 bytes, it shouldn't cross our program. So this is 41 and this is 40. So it's 39 characters plus the new line, so nothing happened. And if we feed it just another one, it should let me see. Yeah, so it needed 41 characters plus the new line. And that's because this local cookie variable is corrupted. Oh yeah, the terminating new line is not copied, so that's the actual size of the overwritten data. So it's 41 characters exactly. And that's because one of these 8-byte characters was corrupted, and when here Ghidra is sometimes changing names to so when the actual local cookie is checked, it is found that it's corrupted, and then it calls the stack fail function. Now, in order to calculate how many bytes you in a in a typical Stack Overflow scenario, you try to override the return function and with your own address on the stack or somewhere else if it is erupting. In order to calculate the return, the offset of the saved return address, you can actually calculate from here, but it's easier to use the GDB, your debugger. Because what's happening here is the RSP is saved on when the call is done, the call instruction, the return function, the return address is saved on the call stack, and then the RBP is set with the value of the RSP, and then the RSP is decreased by 0x by the size of bytes that it's needed for the local variables. The more local variables, the bigger this value will be. And so technically the return value is you need to calculate the address. So in this case is this, the RBP minus 0x30. So we need to overwrite this 0x30 bytes plus the return address, or one or two more 4-byte values, 8-byte values. But in order to make sure you calculate it correctly, you should, because it's easier also, you can use the GDB. And here you can actually set a breakpoint on just before the call instruction, and then hit run. So now here you have you know that the RDI, this is our register, that the register of interest. So in order to get its value, so RDI contains this value, and this should be the call stack address, the address of the buffer that we have. So now if you look into this address, and let's say we want the first 20 I think it is yeah. So these are the first 20 8-byte values at this address in hex format. Uh, so the first 0x20 bytes are, or 32 bytes, are the actual buffer. So this is the area that our buffer is allowed to write its data. And then we have another 8 bytes, and this is the local quickie value. So this is the first 5 values is what Ghidra identifies as the buffer, but it's actually for alignment. This is not used. So this is, if this value is corrupted, then the stack chkfl function is called. And now in order to see the call stack, you hit BT and yeah, this is the address that we are actually so the RBP is at plus 40, so these 8 values are, so RBP points here. And an easy way to find it is actually to set a breakpoint on return. And let it continue. So here now it is about to return to the parent function, and now we can look into the RSP register that is restored. So it was at 128. So this is the return value. So this should be instructions. Yeah, it's libc start main is calling our actual main function. So it returns back here. So it's at this offset 128, and if you look at the data that we had earlier, it is this address actually. So let's go back to where we were on just before the call instruction. So again, no RDI. So the return address is at E128, which is this value, and the actual RBP value is the 120. So from 120 all the way up to E0 E0, so like 10 0x10 bytes more more than this is the local data. So it's these four on these six 8-byte values, and another two, and you can actually see that here, because our local 38 is the variable passed into the gets function, and we have 10 more bytes here, and these are the two variables. So it's one 8-byte value and a 4-byte value, and another 4 bytes for alignment. And this is actually before our value, because it's a smaller value than minus 0x38. It's another 0x10 bytes lower than our the variable of interest. So if we start overriding at F0 offset, then it is we need 40 bytes. It is all these plus another 8 bytes, which is the actual cookie. So we are already at 0x30, and then another 8 bytes, 0x38, and after 0x38 bytes we will start overwriting the return address. And in order to see that, check, let's delete the second breakpoint, and let's place a breakpoint on here on actually here it starts checking the local cookie. And we can actually continue, and we need 0x38 bytes, which is 56, 10, 20, 30, 40, 50, 56 bytes, and let's say FF, EE. Okay. So now the return address will be overwritten by these last 8 characters. They're ASCII values. So when breakpoint number 3 is hit, and we are actually over here just before it checks for the cookie, we can check again how our stack looks like. So this was the address. And the first 7 8-byte values are 0x61, full of lowercase a characters, and then here we have 65. The first 4 characters are 65, and the last 4 are 66, which is 66 65 and 66 are E and F. What we actually expected it to be, and it is at the right place, the 128. As we saw earlier, here this was the cookie and this was the return value at 0x30 from 0x30 offset from the address we are passing to the gets function call. So this is how you actually calculate the return value. Here, because of all the protections, the stack cookie checks and everything, it's more difficult. But if there are no depth stack canaries and ASLRs and stuff, you will see your software crashing and in the actual address that you have overwritten your return address with. So you will actually, instead of seeing the stack smashing, where is it? Instead of seeing this message, stack smashing detected, because there is no stack smashing protection, you won't see it, but you will just see that it core dumped, and yeah, that's all you will see. On the GDB though, you will actually see that your software is trying to execute instructions at this 6566 address. So it will actually go over here, find out that nothing exists, and because it's not mapped, and that's why it crashes the software. If you want to compile it without the actual software protections, you should actually disable ASLR, depth, and the stack canaries. So one option is this, to make you need to disable all the protections and also mark the stack as executable. No stack protector is for the stack canaries, and I don't remember exactly the other options for disable. Actually, disabling ASLR and depth. But here now, since we compiled it with no stack protector, there should be no stack cookie, and we can actually look into that. So here it's the same function, and you can see that there is no no stack protection because it's just called, the get function is just called. And if we go here and actually we need to check the offsets again, and if you run your binary on GDB, so now if you check again the same, the RDI value, there is actually no stack protector, and this time it's at minus 0x28 instead of 38. So our stack actually decreased by 0x10 bytes because there's no stack cookie right now. So in this case, if we overwrite the return address correctly, it should actually jump into this value. Return actually to this value. So this is our buffer again, and I think that this is the return address. If 0x10 bytes are removed, it should be, instead of being at 0x38 from our address, it should be 0x28. So if we move on and override it with 0x28, which is 40, and another 8, so let's say 1, 2, 3, 4, 5, 6, 7, 8. So if we override it with this, which is 40 bytes plus 8 bytes, our return address should be this value in hex. So here we are on the return instruction, and if we look into how our stack looks like, oh, it's terminated. So we can run it again and place a breakpoint on the return instruction. So this is the first breakpoint, and we continue and we give it this size. So now we are on the last instruction of the main function, and if we look on the actual value, so this is the value of the function that it returns to, and if you look closer, you will see that it is one by one all the ASCII characters that we provided. So it is 38, 37, 36 up to 31, which are the actual ASCII values, and here you can see the values, which is, yeah, on the ASCII table it's between 38 and 31. So I think this is the end of the day. We saw two binaries, on one with the stack handler and another one without it, and so how to calculate the return address and what you should overwrite. Do you have any questions? So yes, it is possible to run executables within Ghidra. The actual debugger was published, I think, a week before on a testing version, and we will see how it supports binaries on Windows and Linux also. I mean, the GDB debugger is supported. Something good on GDB? What do you exactly mean? I think there are cheat sheets online, which you can look at. An actual book, I don't know if there is any book, to be honest. Yeah, but maybe there are tutorials online. I mean, for sure there are tutorials online, but I don't know any. I think I learned from some tutorials, plus the cheat sheet, plus their own documentation that doesn't work. So I want to thank Tilda Center again for hosting me, and see you next time.